Good afternoon. Um, let me read a little more from this uh, article in the Toronto Star from almost 20 years ago, April the 12th, 2007. The four, it says Israel Hoffman's four children are the progeny of an accomplished man, a professor emeritus of the University of Toronto, a recipient of the Order of Canada, a member of the Royal Society of Canada, the recipient of many prestigious awards in his field, as well as the Israel Halpern Prize, awarded every 5 years to a promising math researcher. What may have made more of an impression on the four children was growing up in a home where their father arrived at the dinner table. In those days, everyone had dinner together, eager to talk about his work. One summer, he was working on 8 research projects, and the talk at the table was about the progress on all 8. Well, you know, my father was a researcher, but at the dinner table, I think as often as not, I and my 2 brothers got asked what we were doing in school. But we didn't, I don't remember hearing so much about my father's work. So it's 2 ways of proceeding. But anyway, here's a quotation from the older son. I know how engaged he was with the discipline itself. I remember very well the excitement he had when he discovered something new, said Steve Halpern. To find the answer, to now know the absolute truth, and that you are the first person to know it, that is really, truly incredible. Well, so I suppose that the exercises that you're doing, you won't usually be the first person to know how to do it, but still, just finding out, discovering how to do it is already, I guess, can be interesting. That was only part of the legacy of the man who died March the 8th in his sleep at his Midtown home at age 96. Israel Halpern was also a human rights crusader, a one-man letter-writing juggernaut that gathered signatures of Nobel Prize winners and prestigious scientists the world over for close to 2 decades on behalf of a number of political prisoners. Well, I sometimes helped with that. He had a newsletter which I would distribute to mailboxes in various university departments. I was quite interested to, when I went to the chemistry department once, I was quite interested to notice that they had, as well as a considerable number of professors and faculty members, you could tell from the mailboxes they had over 100, not graduate students, but postdoctoral fellows. So math now has a fair number of postdocs, to not comparable to that. Well, one of the scientists that he helped escape from the Soviet Union, from prison, was name was Sharansky. And he's a member of the government. He's a member of parliament now in Israel. But he was in the United States for a while. And while he was in the United States, he was awarded the highest honor, highest civilian honor that is awarded, the Medal of Freedom. He widely distributed those letters and petitions to media and heads of government. Well, I can also cite other members of the university. The letters were cool and cogent and respectful. They were also clear about the fact that the recipient might consider changing his or her illegal and abusive practices because the whole world is looking at. He is adamant and passionately believed in the idea that there should be some way of developing a coherent license. He government to use the human rights that his son Bill. Bill is in the physics department of Northwestern University. Well, the organization was called the International Campaigns for Human Rights, but it was one man. You don't count a graduate student. Okay. One indefatigable man. Cochrane first fought for the release of imprisoned Uruguayan scientist Jose Luis Nacero. Then Soviet scientist Yuri Orlov and Anatoly Nathan Sharansky, and later the torture of prisoners in Chile during the Pinochet regime. And finally, for the release from house arrest, Nobel Prize winner Aung San Suu Kyi, Myanmar, Burma. By the end, he had signed on close to 100 Nobel Prize winners. Oh, I could read from this. Okay, so we've been looking at K-theory and C-star algebras. Basically, C-star algebras are Hilbert space operators. Natural way of looking at Hilbert space operator. And K-theory is more or less the complete story for C-star algebras. So they go together. As it happens, nowadays K-theory is a very broad subject beyond setting Hilbert space and C-star algebra. But it started, as I've asserted before, it started this Hilbert space story, and even Israel Houghton involved in early discussions. Well, from the beginning, I guess it was understood that quantum mechanics is best approached with using the complex numbers rather than real numbers. And the story in Brain Teaser in a book by George Gavinoff, 1, 2, 3 Infinity, that I was talking about last week. That's a good example too of how complex numbers are important. We might be interested in looking up the book 1, 2, 3 Infinity. Well, I guess still very substantial book. It's only $15. I got a copy recently. Give it to the nephew. Read that. But how many people are familiar with the name Richard P. Feynman? Very good. Yeah. Well, he's one of the people who systematically developed the idea of complex numbers. Doing quantum mechanical computations, really made full use of the cancellation properties of complex numbers. If you have real numbers, then it's true that 1 plus minus 1 is equal to 0. That's already interesting. But if you look at complex numbers, then you look at roots of 1, the nth roots of the real number 1, which is also a complex number. Look at the nth roots for any fixed n. What Larry, what do you know about the nth roots of one? Or say the 10th root, say the 10th roots.
Well, I guess it's a complex thing. They're all live.
Yeah, which?
If you look at the complex plane.
Okay, they definitely have to be on the unit circle because you can check that from properties of the absolute value, right? The absolute value is more effective for the nth, and it's a real number. The nth power of the absolute value, then we have to be to the nth power of the absolute value of 1. It's going to have to be 1. And the only positive root 1, 1. So the absolute value of the nth root of unity is going to have to be 1. Is there, can anyone else suggest another interesting fact about the 10th roots of 10th roots of the number 1? Yes, Jack?
You can write down what they are. They're like I, K, I.
Well, all right. Okay. By the way, if you look at roots of polynomials in general, then the Galois theory is quite important way of organizing properties about the roots of an equation, right? For every polynomial real coefficients, we usually take integer coefficients. Galois theory. If you look at the roots of a polynomial, and it's interesting to look at automorphisms. What happens to them under automorphisms of the I guess of the fields that they generate. Of course, fix the integer, for integer will automatically. Okay. But this group, the group that you get, the group which takes the what is the Galois root? It's the automorphisms of the roots. Yeah. The automorph. You look at the algebra. Okay, but you don't have to do a lot of abstract algebra. You just look at the roots themselves. So they're, let's say, n roots, nth roots. It's a degree n polynomial. Maybe some multiplicity, and you can talk about permutations, right? And you know, it's not interesting to look at arbitrary permutations in general, except in most cases it is. In most cases you can look at arbitrary permutations, and that's already all the relations among the roots. What is interesting is if there happen to be algebraic relations among the roots, okay? And then you look at automorphisms. You have permutations which preserve those relations. So the sum of the first and second root, the sum of the first two roots equal to the sum of the fourth root. And you look at permutations that preserve that, right? And that's important. That's the Galois group, and you can tell from the Galois group whether the equation is solvable in a certain sense. So in the general case, when you get all permutations, if it's degree 5 or more, then you can't solve the equation, right? Okay, but in other words, algebraic relations among the roots are important. And what if you take the root? So that's what I had in mind with the looking at nth roots. If you look at the nth roots of Jack, do you want to enlarge on your answer, or Larry? You look at the roots of this equation. X to the nth is equal to 1, and then what algebraic relations are there among the roots? Okay, well, well, okay, that's what you're saying. If you multiply all of them, then what? Actually, I'm not so sure about that because take just square roots, 1 and -1, multiply them, you don't get anything. I'd say you get -1, which is not so remarkable, unless that's always what you got. You got one, that would be remarkable. That would be noted. That would be, well, of course, any relation would be interesting. But we're just trying to see what actually happens. Vincent, if you have a.
No, I mean, I guess it's just as kind of it's just a symmetric group of 10 elements. Like you just take element to its order. I guess take
Okay, so no, come on, you're not saying that you can well actually you look at the roots of one. I can think of one relation, and that relation is preserved by arbitrary permutation. But I don't. I'm not sure that that's the only relation. Okay, and I don't know if the Galois group is just going to be all permutation. Okay? So obviously, I'm a bit rusty in Galois theory. Okay. Anyway, the fact that the Galois theory really goes to town on complex numbers. That's I think it's you could even think of it as pertinent to the course. By the way, does anyone want to suggest the relation that I know this? Okay, might not be the only one. Okay, only one person really is jumping up. Remind me of your name, please.
Admin.
No. How do you spell
D-A-N-N-A-Y.
Tanmay. Oh, yeah.
it? Oh, Tanmay, yeah, okay. I'm not being careful with names. What can you think about relation among the attention groups in one?
They form a group.
That's true. I guess it's true. So, any part of the power is open to one because it's again, right? But that's not just a single equation, right? That's a whole bunch of relation. But relation I'm thinking of, as a matter of fact, doesn't even involve multiplication at all. I think that the multiplicative relations are admissible. I think in this case there aren't any argument. Sorry?
X to the 5 minus
Some of all 10.
Okay, we're looking at 10th roots of 1, right? It's just 10 as just an example. But and there are 10 of them, right? Yes, Jack?
Yeah, like was already suggested, if you have like a root, if you have like a tensor root meaning -1 times that is also going to be a tensor root meaning.
Okay, but you're giving me an argument. You want to pin me down. I mean, is anyone familiar with the rhyme of the ancient paragraph? It's a poem for a ship was being followed by birds. And one of the sailors Elliott. Anyway, serious. Love, everyone's love for the word, but people in time. Then the guy was somehow sentenced to walk around with this bird hanging from the neck. Okay? It's a large bird. Anyway, albatross. But then, and also he was the government was he had to explain to everyone he met what he had done, why he was had to be carrying bird. Okay. But this is it's a principle, it's a very boring story. And actually, to read the poem, it's amazing, really amazingly well constructed. But it's just boring. Okay? It's amazing how something can be boring and still interesting. Maybe there's this book, and maybe there's this Norwegian guy who writes books, novel 1,000 pages or longer than that, and it's completely boring. Okay? But it sells very well. But anyway, that's the maybe that's the story of roots in it. But Archipelago, what was it you were going to say about?
This kind of expressive example can be negative. So not degree then you can really extend the degree now.
Okay, I'm looking for something short and snappy. Let's take square roots. Square roots in the sum of the equal to 1 plus minus 1 is 0. And what is it? What's the good for cube roots? Cube roots, three cube roots. What's the favor? Okay. What about the fourth root? What about the 10th root? Okay, well, it's already getting a bit boring. Right? Okay, but that's what I was thinking. It was, now, maybe I've misunderstood what someone else might say. Doc, were you thinking of something like that?
Yeah, pretty much.
Okay, but of course, it's not that easy to say something, right? Especially if someone is asking you to explain it. Anyway, I'm just this is sort of how I like to try to explore a phenomenon that just looks interesting and I'm not that familiar. Okay. So but it's Feynman was very much emphasizing the idea that complex numbers cancel in all kinds of ways. Okay, and that's what's responsible. That's basically what quantum mechanics is. Theory which seems to point out that nature explained by cancellation of complex numbers to a large extent. Well, he would never try to oversimplify the story. Okay, well, in the case of complex numbers, turns out that there's a fairly simple phenomenon for if you look at projections in matrix algebras, then or even or invertible element projections or unitaries in matrix algebra. And if you just look at the well, the real numbers are a bit interesting too. So you look at the real numbers, then just one projection there is it's well, no, there are two, 0 and 1, 0 and 1. So that's a zero-dimensional sphere, right? There are 2 points. And then if you look at if you look at unitary elements, then there are also 2, plus and minus 1. And if you look at 2 by 2 matrices, the reals, and then how many projections are there? It's yes. Well, you're talking about diagonal ones, right?
Yeah, they're like, I guess, worlds like similarity.
Yeah. Okay. So 0 and then 1 0 0 1. Those will be always diagonal, no matter what you change, how you press the basis, right? No matter how you change the basis. But you look at the diagonal, non-trivial diagonal projections, like 1 0 0, and then that will there'll be other. It's not in the center. If you look at unitary transforms of it, you'll get other projections which are equivalent. And I suppose, in fact, one of the other ones you mentioned was equivalent to it, right? You look at the other diagonal projection, 0 0 0 1. That's equivalent to 1 0 0, unitarily equivalent. And also homotopy, rotate one into the other. Okay, but and this is a projection like matrix that has rank 1, right? Okay. Or the dimension of range 1, acting on 2-dimensional real Hilbert space. But suppose we just look at this set of all projections which are not diagonal. Rank 1 projections are not diagonal. I guess if it's 2 by 2 real matrix projection and it's not diagonal, it has to have rank 1. Rank 0, only one, rank 0, 1, that's 0, and only one rank 2, 1, that's the identical. So you look at the rank 1 projections, there are lots of them. But the matrices have a topological, matrices have a topology, right? Just it's real 2 by 2 real matrices, and topologically it's R to the 4th, right? You look at the convergence of the entries in the matrix. Well, then, if you have any set that has a topological structure, if you look at the set of projections of rank 1, what would it be as a topological space element?
What would be the unit circle?
Well, okay, you're giving more. You're giving you're saying more than is asked for. You're giving it a metric space structure too, right? But if you just if you're just looking topologically, then it's a circle. And now whether it has a natural. Okay, so you're saying that if you look at you're saying more, the difficulty, the thing you're saying more than you're asked for is that it might, if you had only said what you're asked for as a subset of what you actually said, it might have been correct. But then if you're doing additional computations beyond that, then there's a risk that they may diverge from what you want to say. It's okay, but now maybe you're right. Maybe when you put an actual metric, well, one question would be what metric you put on 2 by 2 matrices, right? That's one question. And maybe, wouldn't it be funny if there were more than one metric, more than one natural metric you could put on 2 by 2 matrices, for which the rank 1 projections came out as a circle, as even the unit circle. Of course, it's, well, why are we talking? it's r to the fourth for the whole thing. Why are we talking about r squared? Well, we're talking about self-adjoint elements with trace 1, right? Well, that's two independent conditions. That reduces the degrees of freedom by 2. That reduces the dimension of the space. It's not even a linear space. You say the trace is 1, but it's an affine. You take self-adjoint, I guess it's a 3-dimensional space. That just means symmetric. And that's a single equation. 2 by 2 matrices. There's 2 off diagonal for 3. And trace is a fixed number. That's a certain linear functional. You're taking a hyperplane, or plane, you're taking a plane, pretty good. And this is just linear so far, linear analysis, not talking metric. And might be more than one way of putting a metric on that hyperplane, that plane. And it makes the projections come out in a circle. Now that's a bit of a curious. That would be curious. I mean, I have a vague memory that might be true. Like somehow, but that's not that's a minor, that's a relatively minor point. The main fact is it's a circle, ordinary circle, topologically. Okay, and and if you look at 2 by 2 matrices that are unitary, I wonder what you get. Well, let's do that open for a while as a question. But then let's look at let's review the complex case. Look at if you look at the one-dimensional matrices, 1 by 1 matrices over the complex numbers, then the projections again are just 2 points, 0 and 1. And on the other hand, the unitaries, Charles, what are the unitaries? Well, we're just looking at various star algebras, right? So the real matrices of 1 by 1 by 1 or 2 by 2, and now we're starting with 1 by 1 complex matrix, but a star algebra, right? over the complex number. And the question is, if any star algebra you have unitary elements. So what is the set of unitary? Let's first calculate what the set of unitary elements is, and then see if it has an actual element. Okay. Again, you're putting a metric on it. You're not. I didn't emphasize it, but I was really just thinking about quality. And on the other hand, if you're talking about the complex numbers, no one would try to put more than the standard, anything different from the standard metric on it, right? I think for 2 by 2 real matrices, or even for complex matrices, might be more than one metric one might take. And so it's very interesting to see if it's it would be different on the unitaries or the projections. So let's go to the 2 by 2 case. What would the unitaries, what would the projections be of the 2 by 2 complex case? So they're the same 4 diagonal ones, plus or minus 1 on the, sorry, 0 or 1 on the diagonal. Then now every projection is either has rank in 2 by 2 matrices, either has rank 0 or 1 or 2. And if it has rank 1, again, they're not unique. What would the space of projections be? What would it be as a topological space? And this is now we're over the complex numbers. It's a complex numbers are full of course. Fully or something. Of course. And quite pertinent with the basic productions is. Anyone want to calculate that? Let's see. Yes, occupy.
You have the argument of that will be any equivalent function.
Okay, so you're saying that okay, I'm not sure if this is the easy way of viewing it. You're giving me a statement and a proof. So you said a sphere. Okay, and when you say sphere, I suppose you mean an ordinary sphere. You're not, so when Rishi said a circle, he meant an ordinary circle, right? And now that's a sphere of dimension one. That's a technical word for it. And so when you say a sphere, you don't mean dimension one because that's already been done. Okay, you mean a circle? I mean a sphere of dimension two, right? So that's something that's called a two sphere. Just to avoid any ambiguity. Well, okay, so it's two spheres, and it's well, it's have we seen a two sphere anywhere before? What did quadriticity say for the complex number? Well, for anything, it says you take the double suspension and you get the same K0, right? Okay. Well, what's the double suspension? So what's double? Well, if it's the complex numbers, then you're talking about some topological spectrum of that. You're talking about a point. What's the double suspension of a single point? Well, I guess the single suspension is a line, right? And I mean, if we do it in terms of algebras, if you take the complex numbers and then you take a look at all functions from the line into the complex number, which vanish at infinity, well, then that's a commutative algebra, and its spectrum is a line, locally compact in space. And now, if you take the suspension of that, what do you get? It's functions on the line, and the values are functions on the line, okay? Which vanish at plus or minus infinity. Yes, Jack? Well, I was, yes, right, but do you want to modify that? Yes. If you say open rectangle, then yes. The boundary is not included, right? Then that's the same as the whole thing. Okay, so we're talking about the whole thing. And now forget about the boundary of the rectangle. What happens if you just look at the single point at infinity on the plane? One point in space. What's the 1 point factorification of a line? Right? Do you know? Yeah. Do you know what the 1 point factorification plane?
Yes.
And you're going to say, when you say sphere again, you mean two. Of course, yeah. But because after all, the plane is two-dimensional. Adding a single point, you don't expect that to change the dimension. So I'm probably famous for asking silly questions. All right. Well, but weren't we talking about the two-sphere 5 minutes ago already? And before anyone had mentioned quadriticity, right? So somehow, just talking about 2 by 2 complex matrices, 2 by 2 matrices with complex entries, asking what the projections, non-trivial projections were, not equal to 1. We got a space, which is the 1-point factorification of the spectrum of double suspension of the 1 by 1 games. Well, that's a bit of a mouthful. So, but at least it shows that we're getting the same. Did anyone ever have this experience in school? Some stage of school, maybe an early stage. You'd be looking at a word, and the teacher would say, "Can you use this word in a sentence?" Okay. Well, no, this is sort of a and then the next stage beyond that is if you get 2 words, can you use these? Can you put these 2 words in the same sentence? Well, we just did, right? The 2 phrases. One of them was non-trivial projections on the 2 sphere, and the other was the double suspension of the 1 by 1 meters. You know, join the unit, join the point of infinity, you get 2 sphere. Get 2 sphere both ways. So what this basically says is that well, if you look at take this double suspension of the complex numbers. This was continuous functions vanishing at infinity on the plane, right? If you join a unit to that, you get continuous functions, continuous complex value functions on the 2 sphere. So what periodicity says that well, but then K0 of that, when you take away the unit, that should just be Z, because it should be the same as it is double suspension. It should be the same as for the complex. Then corresponds to that. If you add the unit, then you're getting a Z squared. But the reason to look at the unit algebra is that's how you define K0. To define K0, you have to look at any unit. We look at the algebra of continuous functions on the 2 sphere. Okay, and we're looking, and want to see what K0. We want to see K0. Can we just see K0 by looking at it? If it's complex numbers, it's easy to see K0, right? It's in terms of projections, it's the class of the unit, right? Do you agree with that, Vincent? Anyone want to argue about that? Okay. Has anyone ever watched Monty Python? Okay, so one of the episodes is there's an office where you can go to argue. And you have to pay, of course. And so it shows one guy doing this, and he gets some argument, moderately satisfactory argument for a while. Then all of a sudden, the guy at the desk looks at his watch and says, "Your time is up." The guy says, "No, it isn't." And it wasn't probably. Oh, all right. So anyway, we're trying to find the second. There's a unit. If you continuous functions on the 2 sphere, it has a unit. And that's presumably non-zero element K0. Okay. But that's the one we have to kill. That's the one we have to throw away, right? because to get the double suspension, which is continuous function on the two-sphere vanishing at a point, or equivalent vanishing at the point of infinity when you join the point of infinity. Well, that's we throw away the unit. Well, one unit is the same as the other. It's only one unit. So that Z is not interesting. Okay, what we're looking for is a Z which is a bona fide A0 element for the double suspension. Okay, and to find it, to see it, we had to join a unit, right? So it's supposed to be a projection, value function. It's a projection, supposed to be a projection in the continuous function from S2. 2x2 matrices over the complex number. Okay, looking for squared here. And it actually but it should be nothing to do with the function constant equal to the identity matrix or constant equal to the matrix. I guess the actual unit in the commutative algebra. Obviously, in the commutative algebra, there's only one projection, right? The continuous functions on the two-sphere. The only, just like the complex numbers themselves, the only projections are 0 and 1. And so since the two-sphere is connected, the only function with values 0 and 1, which is continuous, is either constant 0 or constant 1. We have to go to 2x2 matrix. And the question is, so the constant function 1, 0, 0, 0, that would be the unit of the commutative algebra contained in the 2x2 matrices. That's of course. All right. But well, it's a projection. It's helpful. It helps to look at things in two ways. I think it always helps to look at things in at least two ways. There's an expression: there are two sides to any story. Now, it's not always true, but sometimes people say that, and when it's not even true. But anyway, or it's debatable. But in this case, it's not debatable. Here it's it's a little difficult to see what we're looking for here, but here, continuous matrix value functions on the two-sphere. If you want a projection, that means at every point the value is a projection. That means, but it's an order, but we know what the projections are. It's projections in 2x2 matrices over the complex numbers, project non-trivial projections. So it's points on a two-sphere. Okay, so we're looking at the projections. We're looking at functions from the two-sphere into the two-sphere. That's what we're looking at. Okay, and if it were the function constant equal to this, well, it would be irrelevant what the space was. Constant functions on the two-sphere. That's but if you're looking at non-constant functions, well, there aren't that many non-constant continuous functions from a sphere into a sphere. Up to homotopic, how many are there? Well, it's a well-known subject of study, right? You have something that's homotopic to just a single value. But that map you might say has degree 0. Then there's a map with degree 1, the identity map. Okay, map S2 to S2, Z goes to Z. Or I don't know what we should say, it's variable. But that's the trouble with notation-free analysis, sometimes you don't know what to call something. Well, we just call it a variable. But well, okay. I think the point is taken. We have there's a you could map instead of taking the identity map from S2 into S2, you could flip. Okay. If you have S2 sitting in 3 space, you can flip it, right? You take any point goes to its multiplied by -1, every point goes to its opposite. And that's degree, that's a different degree, right? That's degree -1. Is that right? I hope I got that right. Anyway, there are a whole lot of integers. The possible functions from S squared and S squared, they seem to be labeled in a significant way by integers. Well, that sounds like K0, right? The second generator, K0 of the suspension is sorry, K0 of the double suspension. That's the same as K0 of the complex numbers. So we're looking for a subgroup of K0 isomorphic to Z. We're looking at subgroup of K0 of C of S squared, the algebra we're using, right? Isomorphic to Z squared. Well, it looks as if we just take all the different maps from S2 into S2 with different degrees, and that would give us different K elements in a whole discrete one parameter family being indexed by integer. Well, that's how it goes. And so this is a sort of turning bot periodicity into real life, recognizing it in real life. Okay? It turns out that you're going to actually prove this, you more or less have to repeat the general proof of bot periodicity. If we want to actually prove that this identity map from S2 to S2 generates together with the passive unit, generates K0 of these algebras. First algebra of the well, that's a good subject for an essay to struggle with the calculation in this case. We're seriously trying to prove that the identity map is the second generator of K0 of the unital algebra. And it's be done without a whole chapter in the textbook. At least one whole chapter in the textbook. Anyway, this is not just bot periodicity in action. It's actually bot periodicity. This is it. Okay. And except I'm just saying it. I'm just saying that this is true. And by the way, if we look at unitaries, this is projections. If we look at unitaries, is C of S1. Sorry. Yeah. One thing, the bot periodicity says that K0 is the same as K0 of the double suspension, but also says the same as K1 suspension. Okay. So let's see if what we didn't get as far. No, we did. We did K1 of the suspension of the complex numbers is continuous functions on the circle, right? If you join a unit, it's continuous functions on the line vanishing at infinity. Complex value functions. But then if we join a unit, you get continuous functions on the but it turns out that it's continuous functions from S1 to the complex numbers. And we've already identified what the unitaries are. That's another circle. Right? So it's the same. Looking at K1 of S is a very similar picture. We're looking at continuous functions from S1 to S1, or maybe 2 by 2 matrices too. Maybe in this case, to get an interesting one, to get a non-constant one, we We don't need to go to matrices. Not S1 to S1. We can take, we can take the function, we can take the identity map from S1 to S1. Or we have all the other maps, right? It's like analogous to degree. You can look in the circle. You can take Z to the end, Z goes to Z, or Z goes to Z squared, and so on. You get a copy of Z here too. But it's a question of proving that this is K1, the suspension of the complex numbers. Is that actually equal? Is that actually equal to Z? It's the same question here. Is the double suspension of complex numbers, is that equal to Z? In both cases, we've found what the generator is. We've essentially answered the question. To all intents and purposes, we've answered the question. But it's actually this question, and this question, it's easy to go back. It's not deep to go back and forth. It's the same whether this is generated by the identity map here, or whether this is generated by the identity map here. It's 6 of one, half a dozen of the other, but it's a whole year to prove. It's a whole fall. Or you $100 for the book, however you measure it. It's unlimited worry. Okay, but let's come back to this. It's the main point in the course. There are other points I like to think of, other important points.